Good evening, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments, where tonight we're going to take a look at using TI technology to explore applications of integrals. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI technology to make tough-to-teach, tough-to-learn concepts accessible to all my students. I'm really excited to introduce our two panelists tonight, Corey Bobby and Tracy Watson. Corey is in his 20th year of teaching education and currently teaches Algebra 2, Geometry, and AP Calculus. Since joining the T-Cubed community in 2001, he has worked on curriculum development and workshop instruction, as well as creating online courses and videos for TI-Nspire technology. Corey, thanks so much for being with us.
Good to be here.
And Tracy has been teaching geometry, AP statistics, and AP calculus at Benton High School in Arkansas for the past 2 years. Previously, she taught college mathematics courses ranging from basic algebra through calculus for over 15 years. She has been an AP calculus reader for 4 years, which she feels has been the best professional development for teaching AP calculus. She was introduced to the graphing calculator as a teaching assistant in graduate school and hasn't turned back. As a T-Cube national instructor, she enjoys sharing with teachers across the country the appropriate use of technology in the classroom. Tracy, thanks for being with us.
Thanks, Mike. It's great to be here.
We're expecting a large crowd, so your audio is muted. Feel free to send any questions that you have for Tracy or Corey using the Q&A window on the right side of your screen. We'll also be using the chat window to send general messages. As a reminder, this session is being recorded, and we'll provide a link to the event certificate of attendance at the conclusion of the webinar. We'd love for you to follow along tonight. We do recommend, though, waiting for the recording to follow along with your handheld or your software, and that way you can really go at your own pace. You can pause the recording, rewind it, and really take the time that you need to absorb everything that's being shared tonight. We hope you don't have any audio issues, but if you do, try selecting Communicate in the WebEx menu, choose Audio Broadcast, and then click Join. At this point, Tracy is going to discuss our agenda.
Okay, tonight we have some exciting things lined up. We're going to be using some online resources that we're going to share with you, and you will receive them at the end of the evening through a link. One of the things we're going to discuss is the 4 calculator allowed actions. We're going to take a look at them on the 84 and the Nspire technology. We'll take a view of visualizing solids by disk and washers on the Nspire. We're going to look at some student work and talk about what we see there, as well as solving for the average value function using the TI technology. And at the end, the excitement is there's going to be a webinar giveaway, the complimentary registration for the upcoming T-Cubed International Conference.
And Corey is going to discuss our expected outcomes.
Okay, we want to talk about a couple of different things tonight, and the first one wasn't actually on the description, and as we talked about it a little bit before as we were planning, we wanted to we do want to go back and talk about how to use TI technology to solve problems on the AP exam and what you're allowed to do and not allowed to do with that calculator. While we do, Tracy and I do focus on AP calculus, we'll kind of explain the reasoning for that. We're realizing now that not everybody that joins us on these is necessarily an AP calculus teacher, but we do want to talk about good calculus versus sloppy calculus and how calculators can support that. So we're going to try to review some things because I find it this point in the year my students start to get a little careless with their calculators. We're also going to talk tonight about solids of revolution. This is a topic that a lot of students have trouble visualizing, so we're going to have a couple of ways of visualizing them using calculators. We also are going to look at some student work tonight and try to examine the grading standards. And then finally, we do want to talk about the average value of a function and how to examine it graphically and numerically.
Thanks so much. Tracy, it's all yours.
Okay, so we're going to start tonight looking at just very briefly the 4 basic calculator capabilities. These are the 4 things that I allow my students on the calculator portion of my test, the part of my test where they're allowed to have a calculator in hand, that they can do without explaining their work. They must show what they're doing, but I expect them to be able to do these 4 things on their calculator. So the first 2, I'm going to look at the first 2 kind of together, and plotting a graph of a function, looking at an arbitrary window, the best window for their problem, and finding zeros in the function where they're needing that just to solve the equation.
Now, these are 2 functionalities that they should bring into a calculus class. They should have experienced these in a prior course. And these are 2 things they can do without, they don't have to do the algebra to solve an equation. And we do want to talk about how they do this and how they demonstrate this grading later on.
But so right now, what we decided to do first is look at this, these 2 on the 84 calculator. So I have my 84 on the side, and I've got my 2 functions, my f and my g function, and my goal is to solve the equation, to set them equal. And so one of the ways I can do it is using the graphing window, and I'm going to show you that first. Now, I assume that you're okay with graphing the equations, because students should be coming into your calculus class, I hope, being able to take functions and actually look at the graph. So I've already typed them into the Y1 and the Y2. And so if I hit graph, I can look at my 2 functions that are being graphed. There's the first function, the f of x function. Now here comes the g of x function. Now, the one way that I usually have students do this is look at the individual functions, and our goal is to find the intersection of those 2 functions, and that will solve the equation. The component, the capability is said finding the zeros of the function, and you could create a 3rd function, which is the subtraction of your f and g, and actually find the zeros. But I'm just going to choose to do the intersection. I like seeing this on my graph. So to do that on the 84, hit second, trace, and that gives you your calculate options for what we're looking at. And since I chose to do the intersection, I'm going to select number 5.
Tracy?
Yes.
I think, oh wait, never mind. You forgot the cube. It's 2.3 x cubed.
Oh my, yes I did.
One of the participants pointed out that you lost your cube in there along the way.
Oh, that would make a difference. How's that?
It's going to change your answers a little bit.
Oh, and now I deleted the whole thing. Okay, let me just type it all in again.
Well, that's okay. Now, for those of you who may not have worked with me and Tracy before, Tracy and I are actually more than just colleagues. We teach in the same school. We are husband and wife, even though we have different last names. So I like to give her grief whenever I can. So now I have something. So I forgot whoever asked me. I saw in the chat, whoever identified that Tracy did have a typo. I do appreciate that, because now I have something I can tease her about.
And that's going to be the last thing tonight.
Yes.
At least I'm getting it out of the way.
Okay. So, and just so you are aware, Tracy, there were a couple of people who were having sound issues, but we just checked, and it sounds like, I'm sorry, I'm monitoring chat while Tracy is driving, and I'm chiming in. So it sounds like we're okay on the sound issues. So, but there were a couple of people who were having issues early on, but I'm not sure. Everything seems to be working fine. So go ahead on. And now I've stalled long enough for you to fix the calculator issues.
Okay. Now I'm actually, it wasn't a calculator issue, it was me typing in the wrong function. I've got my 2 functions, so I want to find the intersection. One of the things that I think is extremely important about doing this graphical approach and stressing to always look at the graphs with students is noticing that there are two solutions to this equation. You know, because students say, oh, if they find one, then they're done. Well, make sure there's not more than one. So I'm going to hit second trace to bring up my calculate options for my graphing, and I'm going to find those intersection points. Notice when you do that, it's asking you what's the first curve you're working with, and I'm just going to hit enter, second curve, and enter. I only have two curves in there, so that's very easy. And then it wants me to give a guess. So that means it's going to find the closest one to the guess that I give it. This looks pretty good, so I'm just going to hit enter. And I can see, if I wasn't paying attention to my equation, that yes, x equals 0 is an intersection point. So it found the closest one to my guess. To find the other one, the second intersection point, I'm going to still select the first and second curve exactly the same, but now I need to move my cursor over to closer to where that second intersection point may be. And so it's somewhere in this area. And if I hit enter for my guess, I can see my intersection is 2.3.
Now, on this particular problem, the students could actually solve it algebraically. They could subtract away the 4s and factor out a GCF and get their solution. But this is going to be relevant later on because some of the student work we're using uses this particular these equations. And students do not have to show any work, and they can get these answers as long as they write down the equation they're solving, and then they can go straight to the answers. So that's what it says when they can solve or find the zeros of an equation. They can do it without any justification.
Now, the other way from the graphing, I just wanted to show you very quickly because there is not using the graph, but again, knowing that there's two solutions and I'm getting that from the graph is extremely important. So I'm going to get out of the graphing and go to the home screen on the 84. And if I go under math, and if you don't know this is here, even for any algebra pre-calculus teacher, you need to know it's here. There is a solver in the 84. And if I choose solver, I can give it my two functions that I want to set equal to each other. And the calculator, without even doing any work, it will solve these numerically also. If I have them already entered, and I still have to give it a guess because the program that it's running in the background it's doing a numerical analysis type deal where it's only going to find the closest one. And so it's actually using some calculus to find what it is. And so I didn't know exactly where it was, so I'm going to give it a guess of 2. And then when I want it to find it, this is kind of the funny thing on this calculator, up at the top, you'll see press alpha solve. So if I hit the alpha button and then enter, that's how I get it to find the numerical estimate of 2.3 as the solution to the equation.
And so even if you don't necessarily want your kids to do, I use the CAST device in my classroom, and they can type in the equation and it'll solve it automatically. Even if you think the 84 don't realize this is there, I bet some of your students might know that this is there, and you think they can solve equations when they might actually be doing this method, even if you don't teach calculus.
Yeah, and so we really wanted you to see that that feature is in this calculator. The other two basic calculator capabilities, do you want to talk us through those, hon?
Sure. The couple other, so the next one was, the first two were algebraic in nature. They were the creating a graph or solving an equation. They can do those two functionalities without any calculus or without any justification. The other two capabilities that are permissible without any justification are to calculate a numeric derivative, a derivative at a particular value, or to calculate a definite integral. They cannot do an indefinite integral. They cannot do things like, even though the calculator can find a maximum, they cannot find the maximum of a function on the calculus exam with the calculator. So this is one battle that we sometimes fight. So let's do the derivative of the function we were using before, and since we've corrected it, we can use y1. So it is under the alpha command. Or you're going to go through the math menu. There's the n-derived, number 8. I'm sorry, that was the way you were getting it. And there's a template, and if you're familiar with mathematics or with math type or an equation editor within Word, you can we can type in the value. So we do ddx, and here we can use y1 since she defined it in the y equals. So that we would go alpha trace to get the commands, get the functions y1. And we want to do it at what value here? 5. Okay. And that gives us the derivative for that function at x equals 5. And it works in a very similar manner on the Nspire. This templates, there used to be a command n-derive, and you have to do the function, comma x, comma lower bound, whatever it was, and it was all syntactical, but now we've got the pretty print, and we want to make sure that you are aware of how they can do this. Then the next command is how to do a definite integral, and if we go back to the math command, we can choose number 9, function integrate. And again, this one is template driven, and you fill in, and if it looks like what you want it to do, it'll do what you want it to do. So Tracy's going to fill in the limits, 0 to 2.3. And what we're doing now is we're actually trying to find the values for that between the zeros we solved earlier on. This is from the 2014 test. This is question number 1, wasn't it? We're going to be looking at that problem a little bit later on. And so that found the area. Now these commands they're available through the math menu, but if you do alpha window, they're also available here. So this is we also have the logs of alternate bases here, the summations, and some of the other nice commands that are part of the later OS updates on the 84. Okay, so we wanted to reiterate it, and the reason I fought or advocated or brought this in was because at this point in the year, if you're teaching calculus all year, they are mixing their pre-calculus and their calculus, and if you've already done maximums and minimums and things, and you're learning a lot of calculus and integrals and derivatives, they want to be able, my students get confused about what they can and cannot do what they can and cannot do on the calculator. And I actually around this time of year, and I haven't done it in my class yet, but for the last few years, have had a quiz where the quiz isn't about doing calculus or not doing calculus. It's I give them a series of 8 to 12 problems, and they have to tell me if they are allowed to or are not allowed to solve this particular problem on the AP exam by just using their calculator. And it's amazing. They think they can find a maximum. They think they can find an indefinite integral. And those are things you cannot do using your calculator. So I would advocate that you make sure your kids understand and know when they can do these 4 things. And I've also had kids spend 10, 15 minutes trying to solve an equation that they just cannot. They don't know how to algebraically, or it's not even algebraically possible to solve, that you have to get a numerical approximation using the graphing functionality on your calculator. So we thought that would be a good reminder for those of you who are in the AP world. So let's move on to some of the topics for tonight, okay?
Okay, so we're going to switch over to the Nspire. And what we decided to start with tonight is exploring the average value of a function, looking at it graphically and kind of getting our hands on what does it mean to be the average value of the function. So this document, which is up on Math-Inspired, at the end of the evening, Mike will be sending you a link in the chat that you can go download these documents, or if you just search on Math-Inspired, you will find this document. So in this problem, what I'm going to be doing is I'm going to be looking at several different functions, and I'm going to be moving a point And my job is to move this point so that the area of the rectangle matches the area under the curve. And what students are doing is they have a handout, if you choose to do it that way, or if you just want to explore it together, where they're looking at the relationship, looking at the function they've got, and the limits of integration, and the C value for the problem. And so here's my first function. It's a quadratic function. And if you look down at the bottom, below the shaded area, you will see this is the value of the integral of that function from 2 to 5. So the value of the integral is calculated down here. Up at the top, notice it says area is width times height, and underneath it, it's 4.3. So what it's done, go ahead.
So it's telling, I'm sorry, it's just to reiterate and to try to get the kids to understand, we're looking at that bluish area is, or the shaded area is 4.5, and the rectangle currently is 4.3. And we were trying to find a way to make them be the same. We want the rectangle, we're going to change the height of the rectangle. Now if I go that way, I'm making it worse. And then how I keep moving it until I get it to match up. Oh my goodness, hon, you're just really having a hard time. But
I'm close enough. If you want me to get closer, one of the nice things that they put in this document, because it's really difficult to getting it exactly 4.5. I don't think I've done it yet. Oh, I had it. Yes, I
there
did.
You go. Yay.
If you can't get it exactly, I mean, we can see close enough is close enough, but they've also built the document so that you can come over to the Z value and manually change it. So I can manually adjust this value also.
And so what do we actually have here? And the kids can find an average value. You can teach a child to find the average value of a function, but they don't understand what they're doing. What are we actually doing, Tracy? How do you explain this to your kids? Do you have a way?
I get them to look at what we found here. We've got these two different areas, one that's shaded and one is the rectangle. And one of the things I get them to think about is, what is the quote-unquote difference between them? Well, we know numerically there is no difference. And so what it means is we've got this area up here, and they start seeing that that needs to fit into these two, what do you want to call them, open areas of the rectangle.
Those wedges or whatever, yeah. So if we flattened it out, it would look like the rectangle. Mm-hmm. Now, is that the only way, is that the only place that this can happen?
Let's go find out. Because, I mean, that's where I ran into it, and boom, I'm going to stop and I'm done. But graphically, again, thinking about the picture, is that the only time that's going to happen for this function?
And we just went past the other one, and they oftentimes, the average value problems ask you to find the value of C. Now we had, and we should have written down the earlier one, but now we have the value of 2.635. So in this particular example, there are two X values. I don't remember what, I didn't catch what the other one was, 4 something. And it's probably, in this case, it's probably symmetrical, so it's probably
4.366.
Yes, yeah, as I say, it had to be 4.3 something, 4.36. Anyway, and that's only a function. That's only the result because this function has symmetry as well. But we have all of those places, all those X values, and that's why I love this document. Some of the documentation on this talks about trying to figure out when we have an average value of a function and when we don't, and we'll talk about that when we get a couple slides down. But my students sometimes struggle with, why are we finding this C? They can figure out, oh, so what an average value of a function is, but where is, this is the mean value theorem, and there are 2 theorems, well, I guess there's going to be 3, because they're going to talk about L'Hopital's, well, they're adding some things, but they always cite the mean value theorem and the intermediate value theorem, and students mix those 2 up. So I try to make a big deal about the mean value theorem and why this is the case. Boy, you got really good at that, Tracy.
Yes, I did. Okay.
So let's move on to a couple other ones here. So here's another one with a negative, with limits that are negative. And again, if we look at her area is higher, the area of the rectangle is higher, so she's dragging it down, and somewhere around that point, or maybe a little more, somewhere between those two numbers, and we're looking at small differences along the x, is one of the places where that rectangle. Now, where do you think the other one is? We could do it if she was there. Where is the other one without having to drag it along the graph? That's a key conversation for kids too. Once you've got it here visually, we can find both of them just by dragging that point over. So I like to have them have a visual of it and a physical. And if their students have the calculator, they can do this themselves on their personal devices. Or if worse comes to worse, if you don't have it and you only have the one presentation software yourself, you can put this up on a smartboard and let students come up and drag it. But those values are both represented by the intersections of the horizontal line and the function. Let's jump to the one that, is it this one or no? It's this one still has it. They do struggle with that one, but let's do what's the sixth one or the fifth or sixth one? Yeah, this one. Okay. And I know you all, I'm so used to talking and asking my kids, but down here in the South, I'd say, all right, yeah, what do y'all think about this one? So since the only one who can really answer me is Tracy, what do y'all think about this one, Tracy?
Well, something strange is happening because my area of my rectangle is not changing. I'm going to try and get to 14, so I need more area. I need my rectangle to get bigger. Uh-oh, I went too far now.
Well, what's wrong with this function? Well, and I might try to change the thickness or change the color. That little vertical jump right where she keeps moving and jumping on, that's not really part of the graph. What is this graph consist of? This graph consists of 3 horizontal line segments there's, what is it, 4 to 2.5, is that 2.5? I think it's 2.5.
2 and 3 at the heights.
Okay, I know, but the x values, it jumps at the x value of, I'm sorry, it jumps at 2, yeah. It jumps at x value 2, and it jumps at the x values of 4. And when it jumps, there's no, I can't get in between. What I'd really like is, I'd love to have that rectangle be somewhere between where she keeps jumping, but I can't because there is no function in between. And the problem with this is that this function is not continuous. So that's part of the mean value theorem. The function must be continuous. So this example, this is actually, if you read the documentation on this activity, is one of the main purposes of the activity is to try to get the students to understand when we can have it and when we cannot.
And I think it really helps illustrate when you read theorems, those conditions are so important. And here's an example when you let go of one of those conditions, your results, you don't have them. You don't have the conclusion of your theorem.
Okay.
All right. So do we want to move on to solids of revolution?
If you are ready, I are.
I am. Let's go with solids of disks first.
Okay. And I'm not quite to this point yet. But it's coming up. And solids are, you either love them or you hate them. I personally, well, I shouldn't say you love them or you hate them. You can see them or you can't see them. I can see them. I've always had great visual, spatial sense. It's just the way that my brain works. If Tracy.
And I can't. I fully.
So we both, this is, but she can do them, and she can learn to do them, and she has learned to do them. In some ways, I think Tracy makes a better geometry and calculus teacher than me because I can see them, and because I have this talent, I'm like, why can't you see it? It's harder for me to actually slow down and make my kids visualize, I don't want to do this. I just want to jump in and do the math. Tracy feels even more important. And I have learned to slow down and show them. So that's what this does. This gives us some visuals of what a solid actually looks like in a two-dimensional.
One of the things for someone who is impaired this way that I have trouble visualizing these, there are the handheld manipulatives that you can use. My professor had me look at Play-Doh, you know, and build solids and cut them and everything. But then there's the, okay, transferring that to doing the problem and understanding what we're going to see on paper. I still had trouble doing that part. And so this is what would have helped me so much.
So as we go through, we can define a function, and we're beginning with, this example is x squared over 8 plus 1. And it graphs the function. And I'll let Tracy walk through it since this is her baby.
Okay, so we've got our function graphs, and we're going to look at from the A to B, which right now it's set at negative 7.4 and 8. And that is something that we can change. We can change the interval that we're going to be looking at. So I'm going to make it a little bit smaller over on this side and a little bit smaller that way. So that is one thing that you're able to manipulate in this problem. Now, I've got one slice in here where the XC is. That is a different color. And if I change where that's located, part of the visualization is trying to see what is going to happen to that. And so this is going to let me change where that slice is and watch over on the left part of the screen when I start moving that. Oh, it doesn't happen. It happens on the next slide. Sorry. There it is. There's my slice. Sorry. And so I can actually see what the disk area looks like. This is good for just noticing, kind of getting a hint of what's happening to the different disks as you're slicing this solid. Over on this screen, this is the one that I really like, I can actually see the slice, and when I change where my slice is located, the visual changes.
Now I do. Oops, sorry, I'm getting a little echo there for a second. We do have we have a little bit of advice if you want to use this one. They over the years that they've updated the Nspire software, they've changed the way the sliders work and the way they look. And if you download this document, this is the way it would look on the screen when you first download from the TI website. There's that slider is kind of overlapping some of the function, and so Tracy's going to change it a little bit so that we're going to make a suggested change that you, so you might want to make this note if you want to use this, because it makes it a little cleaner on the screen.
If you are over your slider and if you do a right click, we can actually change the settings of the slider, and the only one that I really want to change is the style. I don't want it to be a vertical. I want it to be a horizontal slider. Now, the only other thing, because now it's completely overlapping, it's a much better slider, but if I do a right click again, I can select move and then actually move that slider above. Little slight fix, but now I am happy. I can see everything that I need to be seeing of connecting the disk area to what I'm looking at for my solid.
And it really does actually align with what's happening on the screen. So as you're clicking XC, that point is moving horizontally. XC is moving horizontally. So the slider actually physically aligns with. So it's just something as we were playing with this last night. The versions occasionally go through modifications, and one of the more recent updates did make a change to the slider. So it's not a mission critical thing, but it's just Tracy and I, well, Tracy Tracy's more of a perfectionist than I am, and I completely agree with her on this one. I think it makes it's just a little bit cleaner. So you might want to download it and make that change. It was just a minor change in the settings and then a move of the slider.
And then if you look at what's happening, notice up at the top, it's recording that your radius of that circle that we're now looking at that is a slice is the value of the function at that C. And then at the bottom is actually calculating that area using what all geometry students, we're studying that right now in my class, pi r squared.
Well, all your geometry students know that. I asked my kids the formula yesterday and they didn't. I was a little scared.
Okay.
All right.
So do we want to move to washers?
Sure, let's go ahead. We've got about 15 minutes.
Okay, so for the washers one, Zach's same kind of setup. I like that there's a similarity between these. Again, it's the visual. And so now I've got two functions that I'm working with, and you can change these functions. Once I do this once or twice with students, they usually don't really need to mess with the functions. You kind of get the idea. But look at this visual. I mean, this to me is just remarkable. So now I've got my two functions and got my washer view. And I'm going to, again, just jump over to this view. This is where it got me the idea of changing my slider. This one, it's not in the way, so it's fabulous. And you can change, again, the location of your washer, and you can see how it looks on the three-dimensional image and what it looks like two-dimensionally. It's connecting your two functions, your F and your G, with the two different radii, and reminding them how to actually calculate the area of this function.
Drew, did you want to go back and try to change a function, maybe change the inside radius to something?
Sure.
Because we could define that to just be 1/2, for example, and let them see.
Oops. Take this off. So is that what you want?
Yeah, let's just see what happens if we change the function to 1/2. So that would be a horizontal. And of course, it's going to be a much simpler figure, but I want to see the difference in the function.
So this is a page with some interactive math on it, math boxes, and so I just went and edited it, and I had to hit enter to actually execute that change. Now if I go over to the picture again, that change has been executed. Again, I like this one. And so you can see now that that function, the inner radius, is constant. And you can actually see that happening.
So if you wanted to do the only problem is your function would need to fit. You might have to do some window adjusting depending on the complexity of your function. We were playing with this last night, and we were going to try to put the function that we're going to use in the student work examples into it, but it didn't fit on the window, and it just wasn't worth it. But I wanted you to see that you can change the function, and that was an easy way of changing the function. Plus, I think it's pretty neat to see that what happens if you have an inside radius that's constant. So
yes,
that inner circle doesn't ever change.
Very nice. Do you want to do anything else with that one?
I don't think so. Is there? I thought it would be worthwhile to see the change, and you can do that with the washer one as well. Yeah. But again, you would have to. I wouldn't go too, like Tracy said, I wouldn't go too crazy with it because you don't want to be changing windows, and so pick simple functions that will stay on the viewing window. And then you should be okay. That's why, if you notice, they had the functions were kind of unusual. They were set so that they would, on page, when you first came in, it was a 16th, and I forget what else was there. So if you use this, make sure you play with these math boxes. And again, you just click on the box, click on the function, and then you can change it right here and delete what you want. So I wouldn't mess with this too much because it would go off the window and then make the circles too big. But it is an easy change, and that might be something you practice before you sit down with students.
But the functions they originally pick, again, the idea is just to get them comfortable with the idea of what the method looks like. And then you can focus on the calculus part, the idea of for any function, what would you do? A general F and a general G, that idea is exactly the same. So.
Okay. Yeah. All right, so you want to talk about the, do some motion?
Yes, let's do a little bit of motion. We've got an elevator. And so what we're going to be looking at is multiple representations of vertical position determined by velocity. And we've got a virtual elevator that we're going to look at and see what happens. So our position, h of t, is our antiderivative f, and our initial position we're going to assume is 0. We're going to be changing time by dragging a point along the horizontal axis, or we've also got some arrows that we can do. So here we go.
And again, if you, since that point time is changing horizontally, you could change the arrows like we showed you earlier, the same exact same fixes. You don't have to do that if you didn't want to. Okay, that's fine. Same thing here. If you did do this and you wanted to change that slider, you could save this file and then you'd have your own version, but then of course back on that slide where it says you click up and down arrows, you probably would want to change that to left and right. You don't have to be an author. All of the documents on the Math-Inspired websites or all the TI websites are vetted and their quality. It's just that Tracy and I, as people who do author some of these, we have little preferences that the other authors would be like, you know, you're crazy. And there's some things that preferences matter. And since the action of the object is left and right, my personal preference is that the arrows be pointing left and right. So,
and I honestly did not even think about that, blink at that twice, because I grab my T and I move it.
So it's exactly right. You can go anyway. So now we're actually starting this all the way out at 2.5 seconds. Why don't we start from where we wanted from the get-go, from t equals 0. So you can, the reason we have both controls is when you're dragging, it's hard to control how far you want it to go sometimes, and the slider can get you off of the points and have you pause time, which we can't do in the real world. So if you drag it a little bit, when we start at 0, as time moves, what is happening to the elevator? Well, I'm fine. Okay, the graph is going up, and the elevator is going up. Okay, so that makes sense. I'm fine with that. No worries. Okay, so stop, go back. Wait, whoa, wait. At this point, what do many students think is going to happen to the elevator?
The elevator is going to stop, and it's going to start going down.
Yeah, many of my students think that the elevator is going to start going down. So I want you to stop at this point and make them make a prediction. Okay, what's the elevator going to do? And I always ask my kids, what do you think the elevator is going to do? Don't shut up, make a mental prediction, put it in your head, and now let's see. Okay, everybody think they know what you think, you know what it's going to do? Okay, let's go. And we'll drag it a little more. Now watch what happens to the red dot.
Oh, it's still going up.
It's still going up, and but the graph is going down. Why?
And so this is where students have to remember, this is the velocity function. It's giving you an idea of the speed that it's going, and it's still
speed and direction. So it's
still,
and so.
Go ahead.
Okay, I'm sorry. They have to understand the difference between what they're looking at and the action. They're so used to looking at position graphs that they expect this to be the position, and it's not. When this graph is positive, the object in this case is moving up, or if it was left and right, if it's particle motion along a horizontal line, it'd be moving to the right. When does it change or when does the elevator actually stop is right here at 4 when the velocity is 0. And then at this point, the red dot will start to go down. So we can now go, and if we watch as it starts going slow because the velocity is close to 0, and as the graph gets further away, that red dot will move faster and faster and faster. So in a downward direction. So that's why the slider is there, so she could click the sliders in a uniform way, and we can watch the motion in a uniform way.
And I've stalled, so.
Okay. Do you need to just get off this page, or?
Yep, I think we need to get off this page.
Okay.
Okay, so here's another one, except what is the difference with what I'm looking at now?
Now you're looking at what function? This is h of t.
Okay. Sorry.
And maybe you want to change the order of those two, because that's the position function, and the first one is velocity, or maybe it's better to do it. But they have to understand what they're looking at. Students need to understand, am I looking at the graph, especially graphs, am I looking at the graph of position, am I looking at the graph of velocity, or am I looking at the graph of acceleration even? Many, many times, at least on the AP exam, they're going to be looking at a graph of a derivative. There's many problems where they're looking at a graph of a derivative or of a velocity, and they like to do that on the AP exam so they can ask questions about antiderivatives and about derivatives. So getting kids used to looking at derivative graphs is a big deal, and in making predictions of the antiderivative.
And someone I saw a chat post up that you can animate a point and make it do it itself automatically, and that's true. I like having control.
Yes, the animation, I was thinking the same thing. I almost put that out there too, but I would, yeah, you can do that, and it will play back and forth. It loops though, and sometimes, I would rather it stop. So here we have both the velocity and the height at the same time, and you can control both of them simultaneously by the slider, and we can see what's happening.
I like that they're right on top of each other. We've talked about them individually, and now looking at how they interact together. Because like Corey said, it's so important for students to pay attention to not just what they're looking at, but what it means, and then asking them questions. Which graph is going to help you answer that question? And so reading and interpreting what's being asked and how that relates to what you're given is so important to see if a student really understands what they're talking about.
Okay, Tracy, I think we have about 5 minutes until we need to give Mike back control so he can
we want to look really quickly at a problem. Do we have time?
Yeah, we have about 5 minutes, so let's talk about, this is actually some work. I went through some of my old books, and if you're an AP teacher and you're not aware of it, your school can order the books. You can actually get your student work back, and these are results from some of my students from the 2014 exam. This is the graph clipping problem, and this one, I remember this one was great fun. We're only going to look at part A because this is the average rate of change. So this is the function that
Part C.
I'm sorry. That's actually number 2. That is the one we're talking about. The graph clipping. I'm sorry. So go ahead.
Now, even though we're looking at an AP problem, and we didn't do it this time, last time in the past, I've looked at some of my, I'll call them regular tests, and I have these problems, these type of problems incorporated in my regular test. I didn't find a good one that I was proud of from my stack that I still have at the house. So that's why we decided to use his AP problems. But I know we all put on our regular test problems like this. And so we've got this problem. We're trying to find the time t for which the amount of grass clippings in the bin is equal to the average amount of grass clippings in the bin over the interval from 0 to 30. Now, if you remember, our very first activity we looked at was about doing an average value of a function. So that's why it ties really nice to this kind of problem. Did they really see what's the calculus, get that calculus connection of what it means to have an average amount of grass clippings in the bin over an interval. So we're just going to take that problem only, and now if you look at this function, the A of t, it is the amount of grass clippings remaining in the bin. It gives us the function 6.687 times 0.931 raised to the t. So it's a much more difficult function we're working with there. And so this is the scoring guideline for this part. Out of the 9 points on an AP open response question, 2 of the points they can earn off of this part. And so we can see we've got our average value function here and what our answer should be of when it's, what is the
from 0 to 30.
Yeah, from 0 to 30 is the time interval for which the time that it equals.
Now this case, the reason we brought this one out is this is an operation. This is one of the operations they can do without any explanation. They can type this into their calculator, but they have to keep all of the decimals all the way through a problem, and at the end they must round or truncate. Both answers would be accepted, and they can, but they have to have 3 decimal places. So in this case, either 12.415 or 12.414 were both accepted. I want to show you a couple of my students here. So let's scan to one of my students, and this is great work. They could have used the function label instead of actually writing it out, and I try to get my students to do this. Whatever the equation was, or what was it labeled?
A of t.
A of t. They could have written A of t in there instead of writing the whole thing. And the units are wrong here. In this, Tony, you're right there. The units are wrong, but that part, this particular part, does not have a unit component. So I believe this would have been okay. But every year there is a part somewhere where units matter, and it's usually more related to a problem about rates. So if they're asked to interpret rate, it would be, you know, pounds per day or whatever the case may be. So I don't think units were part of this particular question, although I do notice that they have days there instead of pounds like he should. So the next one, go ahead. This student did an intermediate step and then got a subsequent answer that was so close it would have lost it, and he was, because 12.414. So we picked this one very particularly because he made some rounding mistake. He did a rounding step and then used that again, and it blew up on him. So he lost the answer point. He would have gotten the first point, but he would have lost the answer point because close does not count on the AP exam. And they can round or they can truncate, but they can't go off rounding along the way. So teach your students to keep every decimal and as they go through the entire problem, and then only at the end may they round or truncate. Okay?
And I think both of these problems, I don't know if anyone noticed on the first one, just really quickly, I mean, this one, when I first looked at the first line, I was like, wow, this is great. You know, and yeah, they solved and they have the days there, but there's actually, I don't know if you want me bringing this up.
Yeah, I can see it.
Missing a DT.
Yes.
In their integral. And, you know, as a teacher in my classroom, I say something, you know, get your DT to end your integral, you know, but when you think about the way the points are attributed here, this student does know their calculus. They know what they're supposed to be looking at. You know, it's not perfectly correct, but in the sense of, does the student know the calculus? Do they know what they're trying to solve and able to solve it? Yes.
And so does the second, but because he made a rounding error, he lost a point. We better move on to the last one pretty quick because we got to turn it over to in a couple minutes here.
Yeah.
The other part, this is the one we've actually been working with all along. It's a volume and which are we looking at in this part A? So it's rotated around y equals -2. And if we, let's just quickly look at the scoring rubric. It's 4 points for the integrand for the two pieces having the limits and the answer. And so let's quickly look at the first student example. This student has the two integrand points, and up at the top where he writes the equation, or she, I don't even remember who this is, they must write the equation they're solving, and then they can spit out the answers 0 and 2.3 without any justification. That goes back to where we began. And I had another book, I don't remember if we put it in there or not, where the 0 and 2.3 just appeared out of thin air. Answers cannot appear out of thin air. They must write down the equation, then they can write down the answer. So that's another thing that we see a lot in the grading is bald answers, as they call it, are often disqualified, and they could lose. They might get the 2 integral points, but if they don't get the limit points, they can't get the answer points. So they could lose a lot of points down the line. And out of 45 points, 2 points is significant. So teach them to, if they're solving an equation, write the equation, then write the answer, and that's what we're after. So that's one of the permissible operations, and the integrand, doing the integral, the definite integral is a second. So this is a question that's really calculator heavy, actually.
Mm-hmm.
Okay. What's the
this one, he is wrong. He loses the answer point, and I found out because I couldn't help myself, picked up my calculator. He did the numeric integral correct. He forgot to multiply by pi.
So he would get 3 out of 4.
This one was, let's see.
We have the limits. He subtracted 2 instead of added the 2, right? Is that what happened here?
Yeah, that's what it is.
Sorry. We have because he's subtracting the 2 instead of adding the 2, so we would lose the integral point. So they have to really understand it. I can see why they did this, because the line y equals -2. So, and then I think the last one, we have a good equation. You can tell I harp on how to solve the calculator, how to use the calculator, and that's our answer, isn't it?
Correct.
Yeah, this one's correct top to bottom. Okay, so I think we're at a good stopping point. We need to give Mike back control so he can do his wrap up. Thank you all.
Thank you. It was fun.
Thanks so much, Corey and Tracy. As we begin concluding tonight's event, if you have any last-minute questions for Corey or Tracy, please try to get those asked. I know they'll do their best to get those questions answered. We're really excited to have the T-Cubed International Conference coming to Chicago in early March this year. The T-Cubed Conference is a great way to connect with other educators and go to sessions that might, say, focus on calculus-specific topics. As Tracy mentioned at the beginning of the webinar, we are doing a webinar giveaway tonight for a T-Cubed International Conference free registration. And tonight's lucky winner is Aaron Warnett. So Aaron, congratulations. We'll be in touch over email in the coming days to give you a little more information, but we hope to see Aaron there as well as everyone else. To receive a certificate of attendance, go ahead and click the link in the chat window. That link contains the name and date of tonight's event. Also listed as a link for the documents that were used tonight. If you happen to miss either one of those links, have no fear. You'll automatically get a follow-up email within a couple of days, and that follow-up email will have a link to the recording as well as a link to the certificate and the documents as well. If you're in need of any post-webinar follow-up after we end tonight, feel free to give us a call at 1-800-TI-CARES or drop us an email at ti-cares@ti.com. Thanks so much, Corey and Tracy, for everything you shared tonight. I really appreciate it.
Thanks.
It's our pleasure. Thanks.
Again, thanks everyone. We hope to see you back online next week. Have a great night.